public telephone network is undergoing a massive transformation. Around 80% of the world's backbone networks have already been digitized. However, the local loop, the last mile connection between the subscriber and the network, remains about 93% analog. Digitizing this last mile is one of the biggest challenges in modern telecommunications because without broadband access to every home and office, the internet and advanced applications simply cannot grow. Today's networks are electronic, but the future points toward end-to-end optical or photonic networking, where light carries data from source to destination without ever converting back to electrical signals. The new public network must be intelligent and programmable. From anywhere in the world, any service or feature should be accessible, regardless of which network provider or platform you are connected to. This requires 6 key characteristics. First, very high bandwidth infrastructure to support data-hungry applications. Second, multi-channel capability, meaning one physical medium carries multiple channels of different traffic simultaneously. Third, low latency. Satellite links can have round-trip delays of 500 milliseconds, and today's internet often has 1 to 2 seconds of delay. The new network must minimize this. Fourth, the network must be protocol agnostic, able to handle any data format or protocol through a single interface. Fifth, quality of service guarantees, ensuring that bandwidth, latency, and loss requirements are met for each type of traffic. And sixth, built-in encryption and security to protect data at every layer. As networks evolve, entirely new categories of applications become feasible. Streaming media, online education platforms, and telemedicine consultations all depend on reliable, high-speed connectivity. Interactive multimedia, digital television, and 3D gaming push bandwidth demands further. Virtual reality applications, such as holographic telepresence, represent the most extreme requirements. And e-commerce and mobile commerce continue to grow, requiring networks that are both fast and secure. Let us look at the backbone bandwidth these advanced applications would require. Online virtual reality, including life-size 3D, holography, and telepresence, would need 1 to 70 petabits per second on the backbone. Machine communications for smart utilities, web agents, and robots would require 50 to 200 petabits per second. High-volume computing tasks like 3D computer-aided design and weather forecasting would also demand 50 to 200 petabits per second. And once residential broadband reaches 100 gigabits per second, the aggregate traffic would be on the order of exabits per second. That is 10 to the 18th bits per second, a truly staggering number. To make sense of these enormous numbers, engineers use SI prefixes. Starting from the most common, kilo means 1000 or 10 to the third. Mega means 1 million, 10 to the sixth. Giga means 1 billion, 10 to the ninth. Tera means 1 trillion, 10 to the 12th. Peta means 1 quadrillion, 10 to the 15th. And exa means 1 quintillion, 10 to the 18th. Going smaller, milli is 1000, micro is 1 millionth, nano is 1 billionth, and pico is 1 trillionth. You will encounter these prefixes constantly throughout this course, from kilobits per second for voice calls to petabits per second for backbone networks. Let us review. The public network is evolving from analog to fully digital, but the last mile remains the bottleneck. The new public network needs 6 key features: high bandwidth, multi-channel support, low latency, protocol agnosticism, quality of service guarantees, and built-in security. Advanced applications like holographic telepresence could require petabits per second on backbone networks, and aggregate residential traffic could reach exabit scale. In the next lesson, we will look at the basic building blocks of any telecom network: circuits, channels, lines, trunks, and the different types of network connections.